Alright, welcome back again. So we're going to pick up from part one of isomerism. So we are going to look at stereoisomers. And remember from part one, I had said we have two types of stereoisomers. So the one we will look at first is the geometric isomers, right? Also called cis-trans isomerism, right? And remember, for the stereoisomers, all right. So let me just put a definition. So remember now, with the structural isomers, the way the atoms are connected in each compound is always different. So something about the connectivity is different. For stereoisomers, their connectivity, so the way the atoms are bonded to each other, will be the same. So in terms of the main difference between a stereoisomer and the structural one, in structural isomerism, the connectivity of the atoms are different. In stereoisomers, the connectivity is the same. How they become isomers is the way the atoms are arranged in space. So how they align themselves in space. But the connection will be the same. So for stereoisomers, so these are compounds with the same connectivity of the atoms, but differs in their arrangement in space. Or if I want to say differ in their spatial arrangement, whichever way I want to phrase it. So the point is, they are connected the same, but how they are arranged in space is different. So the two types of stereoisomers, we have the geometric and we have the optical. So we will start out by looking at the geometric isomers. Alright, so as I've stated, geometric isomers occurs in alkenes. And another name is cis-trans. So, simple example, let's look at the compound CHF, CHF. Alright, so that would have been C H F. Alright. So this is our compound. Now cis and trans refer to a particular spatial arrangement. So with the cis, you will have two groups, right? And each carbon atom that are the same. Let me just change this from an F to Br. So on each carbon atom, you must have a group in common or an atom in common. So in this case, the hydrogen atoms, right? So each carbon has a hydrogen atom. Now to arrange it in the two configurations, cis and trans, right? Let's draw up the carbon to carbon double bond, right? And we're not going to draw vertical and horizontal lines. We're going to draw the diagonal lines, right? So like that. So this carbon atom has a H and it has a fluorine. This carbon atom, it has a H and it has a fluorine. So this is one configuration. In the next configuration, right, we draw back the same carbon to carbon double bond. Right? Draw these slant lines. Right? So H, when you do it like this, you can choose to put which one up here and down here. So HF, alright, you can put HF, right? This time, not F, BR. So this time we can put the BR above, right? So this BR is on top and the H is below. Now, first thing, look at the two compounds, right? Remember, the connectivity must be the same, the spatial arrangement must be different. This carbon has a hydrogen and a fluorine. This carbon, it has a hydrogen and a fluorine. This carbon, it has a H and a Br. This carbon, it has a H and a Br. If we should name them, right? Let's see if we can hold. This would have been 1 bromo, 2 fluoro, ethene. Right? If we were to name this, it would have also been called 1 bromo, 2 fluoro, ethene. So you can see that we have the same compounds present, right? This is 1 bromo, 2 fluoro, ethene. This is 1 bromo, 2 fluoro, ethene. So how are the isomers if the name is the same? Remember, the name is the same because the atoms are connected in the same way. However, now, the reason why they are isomers, their spatial arrangement is different. In this compound, the 2 hydrogens are on the same side. But in this compound, the 2 hydrogens are on opposite sides. So this is why it's an isomer. Now, if it was a carbon to carbon single bond, right, it couldn't exist as an isomer. The reason being, when you have carbon to carbon single bond, the carbon atom can rotate. So when it's a carbon to carbon single bond, the carbon atom can rotate. Alright? So because it can rotate, you would be able to get the H up here and the Br down here. However, because it's a double bond, now, this carbon atom cannot rotate. So the double bond, right, it restricts the carbon atoms from rotating. So this compound will not look like this one. So the H will stay up here and the Br will stay here. In this one, the Br will stay up here and the H will stay down here. So that is why, as you can see now, the connectivity of the atoms are the same, but how they are arranged in space is different. So that is why it's a stereoisomer. Now, when they're on both sides, right, the two atoms, the two same atoms, right, or groups are on the same side of the double bond, right? When they're on the same side of the double bond, then we say it is cis. When they are on opposite sides of the double bond, we say it is trans. So this would be cis 1 bromo 2 fluoroethene, and this would be trans 1 bromo 2 fluoroethene. So the cis and the trans, those are the isomers, because based on the spatial arrangement, they are different. So you have the cis configuration and the trans configuration. Alright? So let's work on next example. Alright, so here we have a next example. Alright, so we are going to see if geometric isomerism exists in this compound. So first we need to draw the displayed formula. CH2, that means right here we have a double bond. So we know it's an alkene. So that's the first thing you must look for, if it's an alkene. Because we know if it's not an alkene, then geometric isomerism is out. It cannot be a geometric isomer if it's not an alkene. CH3, CH2. Alright, so here we have our alkene. So remember now what you're going to do when you get a more complex alkene, you're going to find the carbon to carbon double bond. Alright? So ignore everything else. Locate the carbon to carbon double bond. And remember, this is what you're supposed to do. Alright, so carbon to carbon double bond, and you draw slant lines, right? What is attached to the two carbons of the double bond? We have two hydrogens, right? And then you look to the left, well, to the right in this case. What else is attached? So everything here, you put it back. So you have a carbon with a hydrogen and a CH3 group. Then you have a carbon Then you have a carbon with Cl. Why do I have two Cl here? Cl and two hydrogens. On this side, so this carbon of the double bond has CH2 group and a CH3 group. Right? So remember, for cis strands, the same group, so you pick out a particular group that is the same, right? In this case again, it is hydrogen. So they have to be on the same side. So if you get it on the same side, that would be cis. So now we're going to do the same thing over here. Right? But this time it must be trans. So we're going to put the hydrogen atoms on opposite sides. So I just bring this down, so I'm going to bring this group out. So in this case, it's the carbon with hydrogen and CH3. And it is attached to a carbon with chlorine and two hydrogen atoms. And again, over here, it's still a carbon with two hydrogens. Alright? So clearly, you can see, if you look at the double bond again, the the H is on the same side here, so that would be cis, and the H is on the opposite side, so it will be trans. So clearly, you can see that this compound is a geometric isomer. Alright? The IUPAC name, let's see, 1, 2, 3, 4, 5, 6 carbons. So if it's 6 carbon, that is hexene. Double bond, 1, 2, 3. 1, 2, 3. Any direction, it is still at carbon 3. So it is 3 hexene. But if I count from this direction, the chloro is on carbon 1 and the methyl is on carbon 2. So here is the top. So it would be 1 chloro, 2 methyl, X3E, or if I want to say 3hexene, alright? So if you're asked to name the when you're doing geometric isomers, when you're asked to name the compound, you give it the IUPAC name, and then whether it's cis or trans, you place it in front. So for this one, it would have been cis. So it would have been cis. Then you put the name. And this one, you would write trans, and then you put the IUPAC name. So this is cis, 1 chloro, 2 methyl, X3E, and this is trans, 1 chloro, 2 methyl, X3E. Alright, another example. So, final example. Alright, so as usual, we are going to draw the displayed formula. That would be, right, so CH3, CH3, CH2. That means this carbon needs an extra bond, this one needs an extra bond. So it should be a double bond. So let's see if this one exhibits geometric isomerism. So again, locate the double bond. Alright, this is it. So this carbon, it has two hydrogens attached. This carbon, it has a CH3 group here. This is a CH3 group, carbon with 3 hydrogen, right? So if this is one configuration, what are we going to do? If we try to draw it back, right? We're either going to bring up this hydrogen and carry down this one, or bring up this methyl group and carry down the other one. Whichever you do, you won't even know, right? So let's label this HA and this HB for a second. So we bring up HB and bring down HA. If you look at the compound, they are the same. Right? Remember, for geometric isomers, each carbon of your double bond, so we draw up one to compare it with. If it was like this, right? If it was like that now, then you could have geometric isomers, because on each side of the double bond, right, you would have the same group. But look, in this case, the two hydrogen atoms, so the groups that are the same, they must be attached to each of the double bond. So the hydrogens are the same, they are on each side, they are on both carbons of the double bond. So they can be on the same side, or they could be on opposite sides, right? In this case, the two hydrogen atoms are attached to the same carbon. The two methyl groups are attached to the same carbon. If they're on the same carbons, how are you going to move it across? You cannot. Alright? They are attached to the same carbon, there is nothing that you can do about it. Alright? If you move this up and bring it down, it's hydrogen still. So nothing will change. So this is not a geometric isomers. For you to get geometric isomers, the groups that are the same must be on different carbon atoms. So look at the spatial arrangement, right? Why is it not a geometric isomer? The spatial arrangement is the same. So even if you move one group down and the next one up, the spatial arrangement is going to be the same. The spatial arrangement is the same, therefore, cis configuration and trans configuration is not possible. Right? So this compound cannot exhibit geometric isomerism because the groups that are the same are attached to the same carbon atoms. So these two compounds, let me call it compound A and compound B, right? They are not stereo isomers, right? The reason for that, right? One, two groups that are the same is attached to the same carbon atom, right? Alright, so the next reason, so the two groups that are the same, right, is attached to the same carbons. So the two methyl groups are the two hydrogens. They are on the same carbon atom of the double bond. Of the carbon to carbon double bond. So if that happens, the spatial arrangement same, right? And so the cis or trans configuration is not possible. So if you cannot get cis or trans, therefore it is not a geometric isomer. Hence, it is not a geometric isomer. So you will not get cis or trans because the two groups that are the same, they are attached to the same carbon atoms. Once they're on the same atom, you cannot get them across from each other, right? And so, that's why. So that is it for geometric isomerism. We are going to move on now to the optical isomers, right? So just remember, geometric is only for alkenes. So now we are going to look at optical isomers, alright? And this occurs in compounds that has a chiral carbon. Alright? So to get the optical isomers now, right? So this is formed, this is formed from two compounds that are, we use the term non-superimposable mirror images. So this is formed from two compounds that are non-superimposable mirror images of each other. Right? So with the geometric isomers, it must be an alkene. With the optical isomer, you must have a chiral carbon. So optical isomers, they have a chiral carbon, right? And we will look at what a chiral carbon is now. So optical isomers, chiral carbon must be present. If you don't have a chiral carbon, then you cannot be, then the compound cannot be an optical isomer. So it must have a chiral carbon. On the chiral carbon, that is just a carbon atom. So it's just a carbon atom with 4 different groups attached. So the simplest example, we will just have a compound with 1 carbon, and we are going to put 4 different groups on it. No, group can be an atom or more than 1 atom. So we're going to start off simple, alright? So here, it's a carbon atom with a fluoro, a chloro, a hydroxy, and a hydrogen group. Alright? So for a different group, this is a chiral carbon. We say that the 2 compounds are mirror images of each other, right? And the mirror image is non-superimposable. So if this line represents a mirror, then the OH group will be facing each other. And the Cl will be over here, the fluorine and the hydrogen will be in the same position. Now, let's say we just take up this compound as is, right? And try to place it on this one. So if you take up this and just rest it on this, so the carbon atom, place it over this carbon atom. You will realize, alright, let me put the OH group in below